Hi, I want to share how I trained a LLM to play Minesweeper with reinforcement learning. I used the open source GPT model. And yeah, here you can see a little reconstruction of gameplay of the trained model and the untrained model. So basically before and after. Um, you can see here the green gameplays are wins, the red ones are losses, and the yellow ones are wins, where the model just um, revealed a cell at some point that was already revealed, which I allow. So it still wins, but it's penalized a little bit. Um, Looking at these rollouts, we can see obviously that the trained model is much better. It only has one loss against 49 wins. The untrained one, or the before model, has a lot of failure modes. So yeah, we can also reveal the mines from the beginning and look at what the model does. So yeah, it's very straightforward. It just derives um, from the game state what to do next and what cells to reveal. It calls a tool to reveal the next cell, and it's prompted about how the game works. It's also guaranteed in my game that the first reveal is safe. So only after the first cell is clicked, basically, the setup of the mines is fixed, so that the first reveal is always safe. And then there's also a guarantee that that the game can be won with only logic, and there's no guessing involved, just so that the model even has a chance to always win, just by logic. Let's look at some failure modes of the untrained model. So I think this is quite interesting, because we can look at what the model does. So we can see here there's one cell left to reveal, but the model, we can look at what it generated at this point, and it comes to the conclusion that actually all cells have been revealed, even though it's prompted that it itself shouldn't decide when the game is over, but the game decides when it's over. So this is one failure mode. We also have um, bad responses, which in most cases is just we can look at here. So the model comes to some point, it's doing some reveals, and then we can see what it generated here. It's just reasoning. So it's just um, thinking about what to do next, and it's doing this for so long that eventually it's hitting the maximum token limit, and it doesn't even get to calling the tool or making a decision. And so this is um, a another failure mode, which we want to obviously make the model unlearn, because it should make a decision fairly quickly or within this token limit we set. And then it's the obvious failure mode, which is, yeah, here we have one, which is, yeah, just hitting a mine. Um, so yes, let me talk more about how I actually trained this, some stats. So obviously the trained model is has a much better win rate, almost perfect, and also the bad responses and the other failure modes can be avoided entirely just by training a little bit. The training actually only went for 10 steps, and we can see here uh, from these uh, from these charts how it got pretty good pretty quickly. So here the mean reward, um, the minimum reward is -1, the best is 1. So we see the model, yeah, within a few steps learns very well, and then it converges towards 1. And at this point, I will have to make the environment more challenging, use a bigger grid, more mines, or something like this. And yeah, we can also see tool calls going up, but it's obvious because it also, yeah, fails less, so it's doing more tool calls. And the bad responses here really converge towards 0 as well. So the model, yeah, learns to make a decision quickly, and call the tool correctly. Yes, this is yeah, kind of architecture of the training. I used the open source OpenAI model with 20 billion parameters and medium reasoning, and the actual training, the trained model is just a low rank adapter on the model with rank 32 max tokens per turn. The model can generate 4,000 tokens. The usual temperature, the total context is 32k tokens, just because that's the that's the limitation of the model itself. And for the rollouts, so as I said, I did 10 training steps, and for every step, 128 groups are 16 rollouts. So for each group, there was one seed, which ensured that that all these 16 rollouts got the same game basically, and yes, these then sum up to 4,096 rollouts per step. It should be, and then yeah, in each step the model is updated. I'm using importance sampling here because I'm not doing any like sub steps. I'm not doing several model updates per step, so I don't need any clipping like in PPO, and obviously we're using here group advantages to train in a GRPO kind of manner, and with a Atom optimizer. Yes, so looking at the code a little bit, this is, I think, interesting because the system prompt is this. So very simple, just telling the model, this is the game, this is the tool. It should only use this tool to reveal a cell with the row and column index, and it's just getting some context on how the game works. And this is the actual state of the game the model sees in text, obviously. And this would be a state within the game. So here we have the indices, row and column indices. The hashtags are hidden cells. The dots are revealed cells, and the numbers are also revealed cells with adjacent mines in the adjacent cells. So here the true would mean here must be two mines. And yes, so I used Tinker and Tinker Cookbook to actually implement the rollouts and training. I really like their API, and I think they have some really nice abstractions. So this is the main abstraction I used in the rollouts, which is their environment class, and yes, I'm initializing a game here, which is another class which I implement myself or build myself for the actual game state, and then this is the rollout environment. So Tinker Cookbook uses this initial observation method and a step method to call during the rollouts. The initial message chain to the model is just the tool spec. With the tool it can use the system prompt, and then the render, which is then basically this. In the beginning it will only have hashtags, obviously, because all cells are hidden, and then it's generating it's generating some reasoning, and then deciding on a cell to reveal with this reveal tool. And let's look at the step method. So this is the more important part, where we which is called with the response of the model. So this action variable, and we pass the response, and then there's a lot of fallbacks for malformed tool call, not using the reveal tool correctly, or doing odd stuff, which all leads to termination of the game and -1 reward. And then the important part, when everything is fine with what the model decided to do, then this is the important line where the cell is actually revealed in the game state, and the game class, or the Minesweeper class, then actually also checks, is the game now won or lost, or does it go on? If it goes on, obviously the render of the new game state just goes back to the model. But if it's won or lost, then the final reward is here assigned, which is either 1 or -1. And then the token trace is extended by the new by the generated response of the model, by the tool response, and by the assistant header tokens. And I had to do a little workaround with Tinker Cookbook because they're re-rendering the message chain at every turn, which I found leads to just token inconsistencies in the traces. But yeah, that just as a side fact. And then the training loop here is very standard and very simple, thanks to Tinker's abstractions. So I'm just doing the steps here and looping through the batches, and they have this group builder, which you can use to actually do the group rollouts. And I'm collecting all the rollout tasks here and then running all of them concurrently, so all the 4096 rollouts. And then just collecting a bunch of metrics and doing some logging. And the nice thing about Tinker is then this, which is calling this forward backward async method with the training client with your preferred loss function and the optimizer step. And all of this is then actually done on the infrastructure of Thinking Machines Lab, and they handle all the distributed training for you, and you just collect the results and you can save the state for resuming training. And also what I'm doing here, saving the weights for sampling, and then you can actually download the weights and run inference on the trained model, or the with the trained adapter which I actually did then for the rollouts. And then for the next step here, you just load the new sampler, the new updated model to then sample new rollouts for the next step. So this is kind of what I did. All in all, pretty straightforward, and I think very nice that nowadays it's so easy, and can really quickly be done to train models in all kinds of environments. In this case, something like Minesweeper, which is obviously very easily verifiable, and that's why it works so well to train a model to play it. I would go on and train it on bigger grids and more challenging game setups. And all my code is on GitHub. I will add the link, and thanks for watching.